Explanation of light-emitting diode LED. A diode is a two-terminal electronic component that allows current to flow in one direction only. It acts as a one-way valve for electric current, permitting current to pass through it in the forward direction while blocking current in the reverse direction. Diodes are widely used in various electronic circuits for rectification, signal demodulation, voltage regulation, and protection purposes. A light-emitting diode, commonly known as LED, is a semiconductor device that emits light when an electric current passes through it. LEDs have become widely popular and are used in a variety of applications due to their efficiency, low power consumption, compact size, and long lifespan compared to traditional incandescent and fluorescent lights. Here's how an LED works. Semiconductor material LEDs are made from semiconductor materials, typically compounds of elements from the 3D group of the periodic table, such as gallium, arsenic, phosphorus, and nitrogen. The specific combination of materials used determines the color of light emitted by the LED. PN junction. An LED is a type of diode, and it has a PN junction. When a forward voltage is applied across the PN junction, electrons from the N-type region and holes from the P-type region combine, releasing energy in the form of photons. Energy band gap. The energy band gap of the semiconductor material determines the energy, and thus the color, of the light emitted. When the electrons recombine with the holes at the junction, they release energy in the form of light. The color of the light depends on the difference in energy levels between the electrons and holes. LEDs offer several advantages over traditional lighting sources. Energy efficiency. LEDs are highly energy efficient. They convert a higher percentage of electrical energy into visible light, wasting less energy as heat compared to incandescent bulbs. Long lifespan. LEDs have a significantly longer lifespan compared to traditional bulbs. They can last tens of thousands of hours before needing replacement. Instant on. LEDs turn on instantly without any warm-up time, unlike some other lighting technologies. Compact size. LEDs are compact and can be designed into various shapes, making them suitable for diverse applications. Low heat emission. Since LEDs are more efficient, they emit less heat, reducing the risk of overheating in enclosed spaces. Wide color range. LEDs are available in a wide range of colors, including white, red, green, blue, and many others. LEDs are used in various applications, including general lighting. LED bulbs and fixtures are used for household and commercial lighting to save energy and reduce electricity costs. Displays. LEDs are used in digital displays, monitors, TVs, and large-scale video walls. Signage and advertising. LEDs are commonly used in outdoor and indoor signs due to their brightness and visibility. Automotive lighting. LEDs are used in headlights, taillights, and interior lighting in modern vehicles. Backlighting. LEDs are used in displays and keyboards for electronics such as smartphones, laptops, and remote controls. Flashlights and torches. LED technology has revolutionized portable lighting devices with compact, bright, and energy-efficient LED flashlights. The continuous advancement in LED technology has led to further improvements in efficiency, brightness, and color options, making them an integral part of modern lighting and display systems. Semiconductor materials are a class of materials that have electrical properties that lie between those of conductors, materials that readily allow electric current to flow, and insulators, materials that resist the flow of electric current. The electrical behavior of semiconductor materials is highly dependent on factors like temperature and the presence of impurities or dopants. This unique property of semiconductors makes them essential components in modern electronics and various electronic devices. The most commonly used semiconductor material is silicon Si. Silicon is abundant, relatively inexpensive, and possesses excellent semiconductor properties. Other semiconductor materials used in electronics include gallium arsenide, GaAs. GaAs is widely used in high-speed electronic devices, such as microwave and radio frequency (RF) applications, due to its superior electron mobility compared to silicon. Gallium nitride, GaN is gaining popularity for its ability to handle high power levels and its efficiency in high frequency and power electronics applications. Indium phosphide, InP, is commonly used in high-frequency and optoelectronic devices, such as laser diodes and high-speed transistors. Gallium nitride on silicon carbide, GaN on Cc. This combination of materials combines the benefits of GaN with the high thermal conductivity of SiC, making it suitable for high-power and high-temperature applications. Silicon carbide, SiC, is used in high-power and high-temperature applications, such as power electronics and electric vehicle (EV) power systems, due to its ability to handle high voltages and temperatures. Organic semiconductors, these are carbon-based materials used in organic electronics, such as organic light-emitting diodes, OLEDs, and organic photovoltaics, solar cells. Semiconductor materials are crucial for the fabrication of various electronic components and devices, including transistors, diodes, integrated circuits, ICs, solar cells, and light-emitting diodes, LEDs. By selectively doping semiconductor materials with specific impurities, engineers can tailor their electrical properties and create p-type and n-type regions to form diodes and transistors, the building blocks of modern electronics. The ability to control and manipulate the conductivity of semiconductor materials has revolutionized the field of electronics and enabled the development of the advanced technology we rely on today. P-N junction. A P-N junction is a fundamental structure in semiconductor devices and plays a critical role in the operation of diodes and transistors. It is formed by joining together two different types of semiconductor materials, the P-type semiconductor and the N-type semiconductor. Here's a brief explanation of the P-N junction and its behavior. P-type semiconductor. In a P-type semiconductor, the dominant charge carriers are positively charged holes. This type of semiconductor is created by doping, adding impurities to, an intrinsic semiconductor with elements from group 3 of the periodic table, such as boron. The addition of these impurities creates a surplus of positively charged holes in the material. N-type semiconductor. In an N-type semiconductor, the dominant charge carriers are negatively charged electrons. N-type semiconductors are formed by doping an intrinsic semiconductor with elements from group V of the periodic table, such as phosphorus or arsenic. These impurities introduce an excess of free electrons into the material. Formation of P-N junction. When a P-type semiconductor is physically joined or brought into contact with an N-type semiconductor, a P-N junction is formed at the interface between the two regions. Depletion region. At the P-N junction, free electrons from the N-type region diffuse into the P-type region, and holes from the P-type region diffuse into the N-type region. As a result, a region is created near the junction where the charge carriers are depleted. This region is called the depletion region. Barrier potential. During the formation of the P-N junction, a potential barrier is established across the junction due to the differences in the majority charge carriers in the two regions. The potential barrier prevents further flow of charge carriers across the junction without the application of an external voltage. Forward bias. When a positive voltage is applied to the P-type region and a negative voltage to the N-type region, i.e., the positive terminal of a power supply is connected to the P side, and the negative terminal to the N side, the potential barrier decreases, allowing the flow of current across the junction. This is called forward bias, and the diode becomes conductive. Reverse bias. When a negative voltage is applied to the P-type region and a positive voltage to the N-type region, the potential barrier increases, inhibiting the flow of current across the junction. This is called reverse bias, and the diode becomes non-conductive, acting as an insulator. P-N junctions are the foundation of various semiconductor devices, such as diodes, bipolar junction transistors, BJTs, and field effect transistors, FETs. They enable the control and manipulation of charge carriers in electronic circuits, allowing for the design of electronic components with specific electrical characteristics and functionalities. The energy band gap is a crucial concept in solid-state physics and semiconductor materials. It refers to the energy difference between the highest energy level in the valence band, where electrons are bound to atoms, and the lowest energy level in the conduction band, where electrons are free to move as charge carriers of a solid material. In a simplified model of electronic band structure, a solid material's energy levels can be represented as energy bands. The most important energy bands are the valence band and the conduction band, which determine the material's electrical properties. Here's how the energy band gap influences the behavior of materials. Conductors. In conductors, like metals, the valence band and conduction band overlap, and there is no energy band gap. This means that electrons in the valence band can easily move to the conduction band, allowing for the flow of electric current with little resistance. Insulators. In insulators, there is a large energy band gap between the valence band and the conduction band. Electrons in the valence band are strongly bound to atoms and require a significant amount of energy to move to the conduction band. As a result, insulators have very few free charge carriers and are poor conductors of electricity. Semiconductors. Semiconductors have a moderate energy band gap that is smaller than that of insulators but larger than that of conductors. This energy gap allows some electrons in the valence band to be thermally excited to the conduction band, creating charge carriers, electrons, that can conduct electricity under certain conditions. The number of charge carriers in semiconductors can be further controlled by doping, adding specific impurities to the material. In semiconductor devices, such as diodes and transistors, the energy band gap plays a critical role. For instance, in a semiconductor diode, the energy band gap determines the forward voltage required to allow current flow and the reverse voltage at which the diode starts blocking current. In transistors, the energy band gap influences the device's switching behavior and conductivity. The energy band gap also affects a material's optical properties, determining the wavelengths of light it can absorb or emit. Materials with larger band gaps are transparent to visible light, while materials with smaller band gaps can absorb and emit specific colors of light, making them suitable for light-emitting diodes, LEDs, and lasers. Overall, the energy band gap is a fundamental property of solid-state materials that governs their electrical and optical behaviors and plays a vital role in the design and operation of semiconductor devices. Energy efficiency. Energy efficiency refers to the extent to which an energy-consuming device, system, or process can achieve its intended function while minimizing energy consumption or waste. It is a measure of how effectively energy is utilized to perform a specific task or deliver a service. Energy efficiency is a crucial aspect of sustainable energy management and has several benefits for individuals, businesses, and society as a whole. Key aspects and benefits of energy efficiency include reduced energy consumption. Energy-efficient devices and practices help reduce the overall energy consumption, which, in turn, decreases the demand for energy resources like fossil fuels and electricity. Cost savings. By using energy more efficiently, individuals and businesses can lower their energy bills and operating costs, leading to significant financial savings over time. Environmental impact. Increased energy efficiency contributes to a reduction in greenhouse gas emissions and other pollutants associated with energy production. It helps combat climate change and improves air and water quality. Resource conservation. Energy efficiency helps conserve finite natural resources like coal, oil, and natural gas, ensuring their availability for future generations. Improved energy security. Reducing energy consumption and reliance on imported energy sources enhances a country's energy security, making it less vulnerable to geopolitical disruptions. Enhanced productivity. Energy-efficient technologies often lead to improved system performance, productivity, and comfort, positively impacting various sectors such as manufacturing, transportation, and buildings. Innovation and job creation. The drive for energy efficiency fosters technological advancements and creates opportunities for innovation and job growth in clean energy industries. Examples of energy-efficient practices and technologies include LED lighting. LED bulbs are much more energy efficient than traditional incandescent bulbs and last much longer. Energy-efficient appliances. Modern appliances, such as refrigerators, air conditioners, and washing machines, often come with energy-efficient options that use less electricity. Building insulation. Proper insulation in homes and commercial buildings reduces heating and cooling energy needs. High-efficiency heating and cooling systems. Efficient HVAC systems can significantly reduce energy consumption in buildings. Renewable energy sources. Utilizing renewable energy sources like solar, wind, and hydroelectric power for electricity generation is inherently more energy efficient and environmentally friendly than fossil fuel-based power generation. Smart grid technology. Smart grids help optimize electricity distribution, reducing transmission losses and enabling better demand response management. Governments, organizations, and individuals worldwide recognize the importance of energy efficiency as part of their efforts to achieve sustainable development and combat climate change. Energy efficiency measures are continually being promoted through policies, incentives, and educational initiatives to create a more sustainable and resilient energy future. Long lifespan. Long lifespan, in the context of products or devices, refers to the duration or operating time during which the item remains functional and performs its intended function without significant deterioration or failure. It is a desirable characteristic for various products, especially in the fields of consumer electronics, appliances, lighting, and industrial equipment. The importance of long lifespan in products lies in several benefits it offers. Cost effectiveness. Products with a long lifespan generally require less frequent replacements or repairs, leading to cost savings for consumers and businesses over time. Sustainability. Longer lasting products reduce the overall demand for raw materials and energy resources, promoting sustainability and reducing environmental impacts. Customer satisfaction. Consumers often appreciate products that last longer and provide reliable performance, leading to increased customer satisfaction and loyalty to the brand. Reduced waste. Products with longer lifespans generate less waste, contributing to waste reduction and landfill avoidance. Lower environmental footprint. Manufacturing and disposing of products consume resources and generate emissions. Longer lifespans mean fewer new products need to be produced and fewer old products need to be disposed of, thus reducing the overall environmental footprint. Maintenance and downtime reduction. Longer lasting products require less frequent maintenance, reducing downtime and disruption of operations in industrial settings. Manufacturers and designers often strive to improve the lifespan of their products through various means, including high-quality materials, using durable and reliable materials that can withstand wear and tear over extended periods. Robust design and engineering, creating products with solid construction and engineering to ensure resilience and longevity. Efficient cooling and heat dissipation, implementing effective cooling systems to manage heat generated during operation, which can extend the life of electronic components. Advanced manufacturing processes, employing advanced manufacturing techniques and quality control measures to ensure consistent and reliable production. Warranty and support, offering warranties and customer support to address any issues that may arise during the product's lifespan, boosting customer confidence in the product's durability. Examples of products with long lifespans include well-built household appliances, such as refrigerators and washing machines, high-quality electronic devices, like smartphones and laptops, and industrial equipment designed for continuous operation over extended periods. As consumers and industries increasingly prioritize sustainability and cost-effectiveness, products with long lifespans are gaining more attention and becoming an essential aspect of responsible and forward-thinking product design and manufacturing. Instant On is a feature found in various electronic devices, especially those equipped with modern technologies like solid-state components, such as LEDs, light-emitting diodes, and transistors. The term Instant On refers to the ability of a device to power up and be fully operational almost immediately after being turned on or coming out of a low-power sleep mode. In other words, there is no noticeable delay between activating the device and it being ready for use. The Instant On feature is highly desirable for several reasons. User convenience. Instant On devices eliminate waiting times and provide a seamless user experience. Users can start using the device without any significant delays, enhancing productivity and satisfaction. Energy efficiency. Devices with Instant On consume very little power during the standby or sleep mode, saving energy when not actively in use. Always ready. Devices with Instant On are always ready to respond to user input, making them suitable for quick tasks or immediate access to information. Examples of devices with Instant On include modern computers. Many laptops and desktop computers equipped with solid-state drives, SSDs, offer near-instant boot times, allowing users to access their operating systems and applications quickly. Smartphones. Modern smartphones equipped with fast processors and flash memory can wake up from sleep mode almost instantly, allowing users to quickly check messages or make calls. Televisions. Some modern smart TVs and displays offer instant-on features, reducing the waiting time between powering on and accessing content. Printers. Instant-on printers have reduced warm-up times and can start printing documents almost immediately after being turned on. LED lighting. LED light bulbs provide instant illumination when switched on, unlike some traditional light sources that require time to reach their full brightness. The instant-on feature has become an expectation for consumers, as it significantly improves the user experience and adds convenience to everyday tasks. Manufacturers and designers continue to prioritize this feature in their products to meet customer demands and enhance product performance. Compact size. Compact size refers to the small physical dimensions and reduced form factor of a device, product, or system. The term compact implies that the item is designed to be relatively small and occupies minimal space compared to other similar devices or products with similar functionalities. Compact size is a highly desirable feature in many consumer electronics, industrial equipment, and portable devices. Key characteristics and benefits of compact size include: portability. Compact devices are easy to carry and transport, making them ideal for on-the-go use. They are convenient for travelers, commuters, and individuals who need to use the device in various locations. Space efficiency. Compact products take up less space in homes, offices, or industrial settings, maximizing the use of available space. Aesthetics. Compact devices often have a sleek and modern appearance, contributing to an attractive design that appeals to consumers. Integration. Compact size allows for easy integration into various systems and designs, making it suitable for incorporation into complex setups or limited space applications. Energy efficiency. Smaller devices often consume less power, contributing to improved energy efficiency and longer battery life in portable devices. Cost savings. Compact size can lead to reduced material usage during manufacturing, resulting in cost savings in production and shipping. Less environmental impact. Smaller devices may require fewer resources during manufacturing and generate less waste, contributing to a reduced environmental footprint. Examples of products known for their compact size include smartphones. Modern smartphones are designed to be compact, featuring slim profiles and lightweight designs for easy handling and pocketability. Laptops and tablets. Compact laptops and tablets offer portability without sacrificing performance and features. Digital cameras. Compact digital cameras are small and lightweight, making them convenient for capturing moments on the go. Small home appliances. Compact kitchen appliances, such as compact refrigerators, microwave ovens, and coffee makers, are popular choices for small living spaces or offices. Portable audio devices. Compact music players, earbuds, and wireless speakers are designed for easy portability and personal entertainment. Miniature electronic components. In the field of electronics, miniaturization allows for compact components like microcontrollers, sensors, and miniature resistors, enabling the creation of smaller and more sophisticated devices. Compact size is a key consideration in product design and development, as it addresses the needs of users who seek convenience, portability, and efficient use of space. Manufacturers continually strive to innovate and optimize their products to achieve a balance between performance and compactness to meet consumer demands and preferences. Low heat emission refers to the characteristic of a device or system that generates minimal heat during its operation. In electronic devices, heat generation is a natural byproduct of converting electrical energy into other forms such as light, in LEDs, mechanical motion, in motors, or data processing, in microprocessors. The goal of low heat emission is to design devices that efficiently convert electrical energy to the desired output while minimizing wasted energy in the form of heat. Low heat emission is a desirable feature for several reasons. Energy efficiency. Devices that produce less heat are more energy efficient because a smaller portion of the input energy is wasted as heat. This can lead to reduced electricity consumption and lower operating costs. Longevity. Excessive heat can accelerate the wear and tear of electronic components, potentially shortening the device's lifespan. Devices with low heat emission are likely to last longer and have more reliable performance. Safety. In certain applications, such as handheld devices or devices used in close proximity to users, low heat emission is essential to prevent discomfort or the risk of burns. Environmental impact. Devices that generate less heat contribute to a reduced environmental impact by reducing the need for cooling systems and minimizing overall energy consumption. Form factor. Low heat emission allows for more compact and lightweight designs, making devices easier to handle and transport. Various techniques are employed to achieve low heat emission in electronic devices. Energy-efficient components. The use of energy-efficient components, such as low-power microprocessors and power-efficient display technologies, can reduce heat generation. Thermal management. Effective heat sinks, fans, or passive cooling solutions can dissipate excess heat from devices, preventing overheating and improving overall thermal performance. Efficient power conversion. Advanced power management circuits and converters can minimize energy losses during power conversion processes, reducing heat emission. Optimized circuit design. Careful circuit design and layout can minimize resistive losses and optimize power distribution, resulting in lower heat generation. Material selection. The choice of materials with good thermal conductivity and insulation properties can help manage heat within the device. Devices designed with low heat emission are especially prevalent in the electronics industry, including smartphones, laptops, LED lighting, power electronics, and other energy-efficient electronic products. As energy efficiency becomes a more significant consideration for both consumers and manufacturers, low heat emission continues to be a key design goal to enhance performance, reliability, and sustainability. Wide color range. Wide color range, also known as a wide color gamut, refers to the ability of a display or imaging system to reproduce a broad spectrum of colors. It indicates the range of colors that can be displayed or captured by the device, often expressed in terms of the percentage coverage of a specific color space, such as sRGB, standard red-green-blue, or Adobe RGB. In practical terms, a display or imaging system with a wide color range can produce more vibrant and lifelike colors, allowing for a more realistic and immersive viewing experience. The ability to represent a broader range of colors is particularly important in applications where color accuracy and fidelity are critical, such as photography and imaging. Wide color range displays in cameras are essential for professional photographers, graphic designers, and other visual artists who require accurate color representation in their work. Digital content creation. Video editors, animators, and filmmakers benefit from wide color range monitors and displays to accurately view and edit their content. Entertainment. Wide color range displays enhance the viewing experience of movies, TV shows, and video games, making the content more vibrant and visually appealing. Color-critical applications. In certain industries, such as medical imaging, design engineering, and scientific visualization, the accurate representation of colors is crucial for analysis and decision-making. The most common color spaces used to describe wide color range displays are sRGB, Adobe RGB, DCI-P3, Digital Cinema Initiative, Projector, and Rec. 2020, ITUR recommendation. Each of these color spaces covers a specific range of colors and is commonly used in various applications. Wide color range displays are achieved through various technologies such as LED backlighting. LED, light-emitting diode, backlit displays can provide a wider color range compared to traditional CCFL, cold cathode fluorescent lamp, backlighting. OLED, organic light-emitting diode. OLED displays have excellent color reproduction capabilities due to the self-emissive nature of the individual OLED pixels. Color calibration. Professional displays often offer color calibration options to ensure accurate and consistent color representation. High-bit color processing. Displays with higher bit depth color processing can reproduce more shades and gradations of colors, contributing to a wider color range. The advancement in display technologies has led to the proliferation of wide color range displays in various consumer electronic devices, including smartphones, tablets, laptops, monitors, TVs, and digital cameras. As consumers seek more immersive and visually stunning experiences, the demand for wide color range displays continues to grow in the market.